This tree maps the architecture we've built so far. We are leaving the theoretical whiteboard and entering a live, applied clinical loop. We're deploying the third node in our triad. We are applying the Memory-Augmented Agent to operate as a personalized healthcare assistant. It is 2:47 a.m. Deep inside a massive, quiet hospital data center, a critical patient inquiry hits the main server. A vector database lights up with 8 words. Should I be worried about this headache? If you feed that sentence into a standard stateless retrieval augmented generation system, it fails. A basic RAG architecture analyzes the text in isolation, defines headache, and returns generic advice to drink water and rest. It fails because it lacks the context attached to the user ID. The patient is Maria Delgado. She is 67 years old. Her active patient record details a history of hypertension and a recent stroke. Deep in her medication log, there is a time-stamped addition. She started a new prescription blood thinner in March, and across her last 6 months of clinical encounters, she has reported unexplained fatigue 3 separate times. A search engine sees a headache. A memory-augmented agent correlates a sudden-onset neurological symptom with an active anticoagulant regimen and recognized fatigue markers, and it sees a brain bleed in progress. Healthcare data is inherently longitudinal. Chronic care and medication adherence span months and years, making naive RAG entirely insufficient. You cannot manage a persistent condition with an amnestic model. This flowchart details the perception-to-memory loop. A query triggers 3 parallel stores. Working memory holds immediate context. Episodic memory extracts the time-stamped history of medications. Semantic memory pulls clinical guidelines. These streams converge through a re-ranker, filtering noise before reaching the LLM in 2.2 seconds. Memory retrieval consumes 62% of that time budget. In clinical deployments, spending milliseconds to accurately synthesize a patient's history is the only way to ensure safety. The industry frequently claims that simply expanding an LLM's context window solves the memory problem. It does not. The hard part isn't storing, it's forgetting well. This graph illustrates the 2026 BEAM benchmark for clinical AI accuracy. At 1 million tokens, a brute force context window holds stable. But as the patient history expands toward 3 million tokens, retrieval precision collapses. The system suffers a 25% performance drop. To prevent degradation, the architecture forgets noise to preserve the signal. 3 fixes brace the system. First, hierarchical summarization compresses raw encounters into structured abstracts. Second, temporal reasoning sequences events with normalized timestamps. Third, cross-encoder re-ranking slashes false positives via a second-pass evaluation, highlighting critical red flags. Pushing a model to 10 million tokens breaks the AI completely. If you skip these steps, you trigger confident hallucination. The agent retrieves a messy, unranked medication list, misses the actual guideline, and invents a plausible but entirely fake drug interaction. Managing memory requires strict filtration. In a live healthcare environment, a software failure mode is not a bug, it is medical malpractice. This matrix tracks key vulnerabilities. The most dangerous is diagnostic scope creep. To counter this, semantic memory acts as a circuit breaker, forbidding claims. When red flags occur, it escalates to human services. Memory poisoning is mitigated by strict structuring, right sanitation, and per-tenant encryption. Regulatory bodies recognize these risks. Any system lacking architectural guardrails that attempts to guide clinical treatment faces severe FDA scrutiny as an unregulated medical device. Bounded autonomy is non-negotiable. This architecture is no longer theoretical. It is actively funded, built, and deployed by major enterprise players. This landscape splits the market into clear categories, separating patient-facing navigation tools from clinician-facing conversation assistants. In the clinician space, the incumbent is dominant. Microsoft paid $19.7 billion for Nuance, integrating their DAX system deeply into clinical workflow automation to generate structured notes from spoken visits. The primary challenger, Abridge, is highly capitalized to do the same. Abridge raised a $150 million Series C to turn doctor-patient conversations into structured episodic memory. On the patient side, Hippocratic AI secured massive funding specifically to deploy safety-certified bounded autonomy agents for non-diagnostic tasks like post-discharge follow-up. This rapid adoption is fueled by a clinician burnout crisis, costing the U.S. system billions in operational overhead and lost hours. This metric shows the operational goal, an 85% autonomous resolution rate for routine interactions, dramatically reducing bottlenecks in health systems. The macro forces are clear. The global AI healthcare market is projected to reach over $148 billion by 2029, driven by a 36.8% compound annual growth rate. Venture capital has stopped funding basic search chatbots. This timeline illustrates the compression of adoption. Systems went from early-stage pilots in 2023 to widespread enterprise integration by 2026. The technical consensus is absolute, but memory is simply the foundation for deeper reasoning. The tree continues to evolve. The architecture of Agent 03 directly informs our next build. Its semantic tier is literally the seam into Chapter 6. Once you establish a robust database of semantic truth, you require an autonomous system whose sole purpose is to rigorously search, rank, and verify that documentation before the language model ever generates a response. From 30 Agents Every AI Engineer Must Build by Imran Ahmad, available on Amazon and Pact. Full video series at neuralsca. True artificial intelligence in healthcare relies entirely on context. The margin between a polite reassurance and catching a preventable death begins with the ability to remember.